So on this question, we said the correct answer was C. So that's telling us when we come back up here, looking at those limits, you have to look at number 1, or I, x is approaching 2 from the right side. So if x is approaching 2 from the right side, it looks like that limit is going to be a 1, but the actual function here at 2 is -2. So I know 1 is not correct. So then let's look at option 2. X is approaching -5 from the left. So -5 from the left, that's approaching positive infinity, isn't it? So that one is correct. So we know that has to be true. And I always pause here and look at my answer choices, because if I know 2 has to be true, then I know that's gone. And I also know 1 is not correct, so I know that's gone. And so as you go through here, do eliminate your answer choices. And now looking at 3, the limit is x approaches infinity. That is going to be 4. And we see here as we approach infinity, or the end behavior, we do have that asymptote. So if you go back and look here, which of these does not exist? Well, that one's definitely not going to exist, right? And then here, option 3, those are broken there. So that tells me as x approaches 0, yeah, that limit's going to exist. So here you do have to think about, since you did not have a direction, keep in mind you have to look at the limit as x approaches -2 from the left of g of x, and you have to make sure that equals, or does not equal in this case, the limit as x approaches -2 from the right of the function. We've seen this one quite a bit, this type of problem. Now, have we done this specific one? We may or may not have, but we've seen this type of problem, we have seen this concept, and we have a way to solve it. That all we have. So here, whenever I go plug in our 3, we get 0 over 0. So this one we're going to have to factor. This was our cube formula. And so your first parentheses is always asking yourself, what is being cubed minus, because it's minus, what's being cubed. Now inside the other parentheses, don't worry about the signs right yet. I'll put back in the signs. Let's generate our terms, because there's a nice pattern to generate these terms. We will square this first number. We will multiply these two, and I ignore the sign. Don't pay any attention to the sign. Just multiply those two, and then you square the last one. So it is square, multiply, square. Every time. Never changes. The last term is always positive, and then this other term is always the opposite sign from what you started with. Okay, now on the bottom, that's the difference of 2 squares, x minus 3 times x plus 3. And here, those are going to cancel. And now that we've factored and canceled, we go back and reevaluate that limit. And we're reevaluating x squared plus 3x plus 9 over x plus 3. And if we plug in 3, it looks like we have 9 plus 9 plus 9 over 6, is it? So 27 over 6, which is 9 halves. So we're going to attack this portion first. Okay, so the limit as x approaches -1, or no, +1, sorry, from the right of f of x. So the limit as x approaches 1 from the right of f of x. What do we have a graph of? Is that not f of x? How do I know that? Well, it states it right here. I promise you, you've been told. Now, what is the limit as x approaches 1 from the right over here on this graph? Look at, we're coming in from the right. Y'all agree? So it's -1, right? Yep. So I know that's going to be -1 plus, well, 3 is 3 no matter where I see it, whether you're at Walmart, Dollar General, dirt cheap, 3's 3. And so now let's go ahead and plug in over here, right? Because that's going to be your next limit. What are you going to get when you plug in over there? Square root of who? 9. So what's my answer? 8. -1 plus 3 times 3. So that's going to give us 8. Okay, so question 5. Limit as x approaches c of f of x equals L, where L is a real number. Which of the following must be true? Which one has to be true beyond a shadow of a doubt? So they're telling us that this limit exists, right? If that's here and it equals L, which is a real number, if that limit exists, what did you do to prove that it exists? How do you know it does exist? The limit as x approaches c from the left of your function would have to equal what? L. And it would also equal the limit as x approaches c from the right of the function. That has to be true before this will ever be true. Now, does the function have to equal L? No, it does. It could, but does it have to? No. So our correct answer would be A. Okay, on number 6, if we substitute in our -2, we are going to end up with the square root of 1 minus 1 over -2 plus 2, and that's going to give us 0 over 0, which means we need to factor or rationalize. Something's going on here. So we're going to rationalize. So I have the numerator 2x plus 5 minus 1 over x plus 2. And now I'm going to multiply top and bottom by the square root of 2x plus 5 plus 1. We're multiplying by the conjugate. And again, save yourself some time when multiplying these things out. Our middle term up here, when I do my process of foiling, the outer and the inner are going to cancel each other out. So we're just going to focus on the first and the last. And if I multiply the first two things together, we're going to get 2x plus 5. And if I multiply the last two things together, I get -1. And all of that is over x plus 2 times the square root of 2x plus 5 and then plus 1. Notice the bottom, we did not multiply it out. It's not always the bottom, it's just wherever you did not have a radical to begin with. So here, simplifying this down, we can combine our like terms. We have 2x plus 4 over x plus 2 times the square root of 2x plus 5 plus 1. And now it looks like nothing's going to cancel. However, we can factor out a GCF in the numerator. We can take out that 2. And notice we have x plus 2 left over x plus 2 times the square root of 2x plus 5 plus 1. And now we can cancel those x plus 2's. And we're ready to go back and reevaluate our limit with this portion that's left. So let's go ahead and go back, and we are going to sub in -2. And if I do that, then this limit here would then become 2 over the square root of 1 plus 1. So it looks like that's all going to reduce down to be 1. Okay, for this problem, again, if we substitute in our 0, we are going to get 0 over 0. And 0 over 0 tells us we need a factor. In the numerator, it looks like we have a 3x cubed. And so what's left over is going to be x plus 3. In the denominator, we have an x cubed. And what is left over is going to be a 5x plus 3. And so now notice these x cubes are going to cancel. So I have 3 times x plus 3 over 5x plus 3. And now we can go back and reevaluate our limit as x approaches 0 of 3 times x plus 3 over 5x plus 3. And so substituting in here, we're going to get 3 times 0 plus 3 all over 5 times 0 plus 3. And so in the numerator, it looks like we're going to get 6. In the denominator, 3. So that's all going to reduce down to give us 3. Our next problem, we are looking for our limit as x approaches 2 of this function. And so if we go ahead and find the value here, then notice that the limit as x approaches 2 from the left and from the right, because again we were not told a specific direction, so we have to come in from both sides. And the intended y value looks like it's going to be 3. Now we see that the actual function's value is something else, but with limits we're looking for the intended y value. And so it looks like we're going to substitute in a 3. So this is going to be the square root of 6 times 3, and that's going to give me the square root of 18. And then that will simplify down. Remember, you would break that apart to 9 times 2. So that's going to be 3 times the square root of 2. Okay, on our free response, and we did not get to this part in class, and it wants us to see if these two things are equivalent. So what we're going to need to do is come over to the side, and let's see if we can't find h at 2. So remember the notation for h at 2, that's just meaning substitute in. And if we do that, then we end up with 3 times 2 squared. So we end up with 3 times 4, which is 12, minus 10 plus 2, all over 2 squared minus 1. So in the numerator, it looks like we end up with 4 over 3. Now, if we look at our limit, and again, the limit as x approaches 2, now we're not given a direction, so it's okay to go ahead and subtract in. Now, if we don't get a nice, neat number, that's when we need to go back and look at maybe some factoring or rationalizing or plugging in maybe a 2.001 or something like that. But always go to substitution first. Well, notice you're still plugging into the same function. You're still looking at h at x. And so if I substitute that in, again, I'm going to get 12 minus 10 plus 2 over 4 minus 1. So once again, I get 4 over 3. And so this justify your reasoning is shown here in your work. All you need to do is come back and say yes, or you can say therefore yes, whichever. But yes, h at 2 is equivalent to the limit as x approaches 2 of h at x. And that would get you your full points. Okay, now let's look at part B. Part B asks us to find the limit as h approaches 1. Is that value the same as h at 1? And you need to justify your reasoning based on a graph of h of x at 1. So that's kind of leading us to a hint at what might be happening with this, especially if it says justify your reasoning based on this graph. Now, it doesn't necessarily mean that you must draw a graph. It means that they want you to interpret what might be going on graphically there. So if I want to find our limit as x approaches 1 of h at x, then of course I'm still plugging in, so I have 3 minus 5 plus 2 all over 1 minus 1. And so if I go through here, that looks like you're going to get 5 minus 5. So we're going to get 0 over 0. So it looks like we are going to have some kind of removable discontinuity on the graph of h at x. So let's come over here to the side and do some factoring. And so we have 3x squared minus 5x plus 2 over x squared minus 1. Quick factoring here, 3x. Our signs are the same and they're both negative. And so x minus. And we're going to have 2 and 1 there. And so on the bottom, we're going to get x minus 1 times x plus 1. And this is going to show us what kind of discontinuity right there. We're able to cancel, which should be the case here. And so really graphically what's going on is h at x has a removable discontinuity at, and notice we canceled out x minus 1. So if you take x minus 1, set that equal to 0, or notice if I plug in 1 and 1 here, that's causing the zeros over 0. So we can say at x minus 1. So now we can go back and first of all find our limit. So we do need to reevaluate that. We have the limit as x approaches, what was it approaching? 1. And now we have our reduced function, 3x minus 2 over x plus 1. And when I sub in a 1, then I'm going to get 3 minus 2 over 1 plus 1. So our limit value is 1/2. So that's telling us where that point of discontinuity should be. So now we're going to take this and we can justify here that the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right. And also notice it's saying, is the limit the same as h at 1? And the answer there for sure is going to be no. And let's go ahead and say that the limit as x approaches 1 of our function h at x, you don't have to rewrite all of that, does not equal h at 1. And the because is that removable discontinuity. Because at x equals 1, h of x has a removable discontinuity. Okay. And finally, the part that most of us really don't like, and that's going to be trying to sketch the function given all of this information. So I would go through here and see if I could not at least identify some for sure points. And what I mean by for sure points, that means something like this. That means the ordered pair -2, -3. So I know no matter what, I have a for sure point right here. That I know is true. That's the first thing I would go look for. The second thing I would go look for would be any kind of asymptotes, vertical or horizontal. A big hint that we have a vertical asymptote is going to be right here, because as x approaches 2 from the right and 2 from the left, look at what those y values are tending to. So that's telling me that here at 2, I should have a vertical asymptote. So I'm going to fill in that vertical asymptote. And notice what this is saying, that if I'm coming in from the right, I'm tending toward a positive infinity. So I know I've got something like this going on. Now, I don't know that exact thing. I'm just doing a sketch, nothing perfect. And then over on the other side, I know f at -2 is 3. So whether or not we go through that point doesn't matter. We don't know where we do go through that point at. If you want to incorporate it, great. If you want to leave an open circle somewhere up here and then go ahead and do something like this, you're welcome to do so. Now, we've also got, let's see, the limit as x approaches -2 is for sure 4. So that's going to change a little bit over here. At -2, I've got to be at +4. Since this is a for sure limit, you need to think of this at -2, 4. You've either got an open or a closed circle there. Since you already have a -2, it's going to have to be an open circle. So let's go back. Notice how I'm having to erase, and that's okay. Sometimes that happens. So up here at -2, 4, I know I've got to have an open circle there because that limit's got to exist. Now, what else have I not used? I've not used this one. This looks like it's going to be a horizontal asymptote. So this is saying that as x approaches -infinity, my y values are approaching 0. So I know I have a horizontal asymptote somewhere through here. Yes, it's okay to cross that horizontal asymptote. Nothing wrong with that. In the middle, this is talking about the end behavior. So at the ends of the graph, you don't need to cross it. So whether or not I incorporate this point down here doesn't matter. I do need to incorporate this open circle. And I know I'm tending toward -infinity from the left. So I know I'm probably doing something like that. And then this has got to come back down and run parallel. And they didn't give us much more on this side, so I'm just going to make that one do this.